Swayam Prabha. Digital India. Educated India.
Okay, so good morning. So what I'll be discussing today is this lower bound proof for parity. So in fact what we will show is something more general, that we can give a lower bound for any mod p function, okay, where p is a prime, and this result was due to Razborov and Smolensky. In 87. So basically they had independently, I mean not independently, but actually Razborov had given the proof to show that the parity function, he had given a lower bound for the parity function, and then Smolensky actually extended it to all general primes. In fact, one can actually show it to be even true for prime powers. Okay. So once we see the proof, that will become clear how it works. Okay, so I'll start by defining this class. This is borrowed from Aurora Barak's notation. So ACC0 M1 up to Mk. So L is said to be in ACC0 M1 up to Mk if there exists a polynomially bounded constant depth circuit family, okay, say Cn, consisting of unbounded or unbounded and not and okay, mod M1 up to mod Mk gates. Okay. So basically accepting L. So L is in this class ACC0 M1 up to Mk. If we basically have a AC0 circuit which additionally contains these mod M1 up to mod Mk gates. Okay. And okay, let me just for the sake of completion also define this function, because we will be talking about this. So I will define this mod, let us say P of x1 to xn is equal to 1 if sigma xi mod p is not equal to 0 and it is equal to 0 otherwise. So this is the convention that we will follow, that if the sum modulo p is non-zero, then the function evaluates to 1, otherwise it evaluates to 0. Okay. So, and so basically so this is the function, and I will use this mod in small letter to denote the corresponding gate. Okay. So that's it. So now the theorem that we will be proving due to Razborov and Smolensky is that for distinct primes P and Q, mod phi is not in ACC 0 Q. Okay. So this is what we will be proving, and actually, as I said, that you can actually extend this to not just primes P and Q, but also prime powers. Okay. So that will be clear. So for the sake of simplicity, what we will show is, for a specific case, we will take P to be 2 and Q to be 3. So what we will show is, so we will show a simpler version, that is, we will show that mod 2 is not in ACC 0 3. Okay. So even if you have mod 3 gates in the circuit, in an AC 0 circuit, it cannot compute parity. So mod 2, just note that it is basically parity. Okay. So how do we prove this? So the proof is actually kind of similar to the monotone lower bound for click, in the sense that we use this approximating idea. So what we will do is, so it goes in 2 stages. First we will show that these circuits can be well approximated by polynomials of low degree. So polynomials of a certain degree. So these circuits can be approximated very well by polynomials having some low degree, and then we will show that if we consider polynomials of low degree, then basically mod 2 cannot be approximated well, okay, polynomials of low degree. So basically to approximate mod 2, you need degree to be high enough, and then combining these two, it would imply that, well, the only way in which you can have a AC 0 circuit, well, I should not call it AC 0, but the only way in which you can have a circuit, a constant depth circuit, basically a constant depth circuit, is if the size of the circuit is exponential. Okay. So let me just write them formally, what I mean by these two. So if f can be computed by an by a, let's parameterize it, by a depth d circuit having size s and gates. So we have unbounded OR, unbounded AND, NOT, and mod 3 gates. Then for all epsilon greater than 0, there exists a multi-linear polynomial P over the variables x1 up to xn such that probability that for a random x P of x is not equal to let me just rephrase this. So, I want the degree also to be given here. There is a multilinear polynomial P having degree two log s by epsilon whole to the power d over f3. So, there exists a multilinear polynomial P having degree this over f3 such that okay, instead of probability I can actually write it in terms of the actual number such that P is not equal to f on at most epsilon times 2 to the power n inputs. Okay. So, essentially just this is saying the same thing, that well, if I take a function which can basically for which there is a ACC 30 circuit, okay, I am parameterizing the size and depth here as well, that the depth is d and the size is f, then there is a polynomial having degree 2 log s by epsilon to the power d which actually well approximates that function. So, basically it disagrees with the function on at most an epsilon fraction of the inputs. Okay. And the second lemma is basically that mod 2 does not have good approximation. So, P is a multilinear polynomial over f3 having degree at most root n. Okay, so, if P is basically a polynomial of not too large degree, then P of x is not equal to mod 2 of x. So, again when I say x here I mean the vector x, it is the same thing here as well. For at least uh, 0.155 fraction of the inputs. Okay. So, basically they will agree on at most 85% of the inputs. Okay. So, they will have to disagree on at least 15%. And now if I combine these two, so let us assume that lemma 1 and lemma 2 are true. So, combining lemma 2 and 3, what we get is that, well, if I have to have a circuit for mod 2, okay, that consists of AND or NOT and mod 3 gates, then so the degree here is 2 log S by epsilon whole to the power d must be greater than or equal to root n over here. Okay. And now if I simplify this, what we get is well, log S by epsilon is greater than n to the power 1 over 2d by 2, which implies that S is greater than 1 over epsilon 2 raised to the power n to the power 1 over 2d by 2. Okay. So, basically if d is constant, then the size must be exponential. Okay. So, this is the general approach. Okay. So, now how do we prove both these lemmas? So, first let us look at lemma 1. So, what we will do is we will show how we can, so what do I want to do? I want to build a polynomial corresponding to this circuit, okay. And I do not need to get a polynomial which is exactly matching that function, but at least it should match on a high fraction of the input, okay. So, basically it can approximate. So, basically I want a polynomial which can approximate this function well enough. So, to do this, and because this function is represented by a ACC 03 circuit, what we will show is that we will show how we can approximate each and every gate that is present here, how I can approximate the AND or NOT and mod 3 gate. So, once I do that, and then I can basically count how much error occurs for each of those approximation, and then sum it up over the entire circuit, and that is the idea of the proof. Okay. So, how do we go about doing this? So, okay. So, to prove lemma 1, just one second, I will just use another result. Let me write that first, let me prove that first. Let us state this lemma. So, for every input distribution on 0 1 to the power n, and for all epsilon greater than 0, there exists a multilinear polynomial P such that polynomial P over F3 having degree at most or let me just use the order notation here, log of 1 over epsilon, such that probability that OR of xi not equal to P of that input is at most epsilon. So, essentially this lemma is saying that, well, there is a polynomial of reasonably bounded degree which approximates the OR function quite well. Okay. So, essentially yeah, so basically it will disagree on at most epsilon fraction of the inputs. Now, so let me just okay, so before getting into the proof of this, let me just give a small note. So, how can we approximate the OR function using a polynomial? So, one very obvious way to do it is to consider this polynomial, right. So, let us say if I have okay, let me write this as P hat. So, I can define P hat of x1 up to xn as equal to 1 minus is this correct? So, let us just see. So, if all the xi's are 0, so if the input is 0, okay, then this product will evaluate to 1 and therefore, this polynomial evaluates to 0. Okay. And if any of the xi's is 1, then this product evaluates to 0, because then there will be a term here which evaluates to, I mean which is 0, therefore, the product is 0 and therefore, the polynomial evaluates to 1. So, this is a polynomial which exactly which is exactly equal to the OR function, but what is the degree of the polynomial? Unfortunately, degree of P hat is equal to n. Okay. So, that is too large for us. Okay. So, essentially the idea of this lemma is that how can I approximate the OR function using a smaller degree polynomial. Okay. So, how can I approximate the OR function by this kind of, okay. So, let us say if I allow it to make some constant fraction of error, then the degree should be constant as well. So, let us see how we can do this.